Okay, so basically, this is CH350 biochemistry. I'm just going to do a physical biochemistry review. This is going to be the first chapter before we head on to new material. So basically, this note is going to cover energy conversion, types of cellular work, thermodynamic laws, redox, chemistry, and ATP synthesis. The key points of this lecture is that photosynthesis stores solar energy as ATP or NADPH. Thermodynamics keeps cells far from equilibrium. ATP hydrolysis powers cellular work. Okay? Now, energy conversion in biological system. We have energy, which is a process by which organisms transfer one form of energy into another to sustain life. We have the sunlight captured by photosynthesis, stored as chemical energy such as ATP and ADPH. The stored chemical energy drives three major types of cellular work. We have osmotic, chemical, and mechanical. Looking at that figure, we have those types of work. Osmotic work is active transfer, where we use energy, such as ATP, and basically it maintains, so in the form of maintaining differential solute concentrations across the membrane. Chemical work is basically biosynthesis and degradation of biomolecules. Biosynthesis is like anaplasm. We are making biomolecules from macromolecules. Degradation is cataplasm. Mechanical work is basically muscle contraction, like movement and mobility. I've got the types of work in the cells right here. So osmotic work maintains solute on opposite sides of the membrane, such as ion pumps. We have ATP hydrolysis, which supplies the energy to move those substances against their concentration gradients. We have chemical work, biosynthesis, meaning anaplasm, builds macromolecules, and then we have cataplasm, which breaks them down, involves linear, forked, and cyclic pathways with ATP, ADP, and inorganic phosphate turnover. Finally, we have mechanical work, muscles contraction, and cellular motility. So energy from ATP hydrolysis powers filament sliding in muscle fibers. We have homeostasis versus equilibrium. Basically, homeostasis is highly ordered. It's steady internal state, such as temperature, biomolecule concentrations that require continuous energy input. So homeostasis requires energy, while equilibrium does not require any external energy. So equilibrium is basically a state where forward and reverse reaction rates are equal, leading to no net change in concentrations, so we don't require any energy. Living organisms stay far away from equilibrium to maintain order, while non-living systems tend toward equilibrium spontaneously. Now, talking about the thermodynamic laws, the first law, which is the zero law, it's telling me that two systems are in thermal equilibrium with a third system. They are in equilibrium with each other. First law tells me energy cannot be created or destroyed. It's only transferred. We have the net heat is equal to net work. The second law is basically telling me entropy. Entropy is basically the randomness or disorder of a system. So entropy of an isolated system increases. Spontaneous processes increase total entropy. Entropy is defined by the letter S. Delta S is entropy. And then we have the final law of thermodynamic laws, which is the third law. It's telling me that as temperature approaches absolute zero, so as it goes down and it gets colder and it goes below absolute zero or reaches absolute zero, then entropy where approaches a constant minimum. Meaning, let me explain that law a bit. So basically, when we reach absolute zero, the particles or like the molecules cannot move. They have no thermal motion, so they are not moving, meaning that entropy is going to stay in one way, and that like the entropy will stop decreasing and it will settle at a fixed and lower value. Okay, now talking about redox coupling and energy transfer. So redox reactions is basically the transfer of electrons from an oxidized species, meaning loss, to reduced species, meaning gain. So oxidation reduction pairs are linked to create redox circuit that releases energy for chemical work. Okay, so right here, reduced, when we say reduced, what we really mean is that we're gaining an electron. And when we say oxidized, what really means is that we are losing an electron. Okay, just keep that straight. So now right here we have compound A, which is oxidized and a reducing agent, and then we have compound B, which gains electrons. It's reduced and oxidizing agent. Okay, now moving on to some mnemonics to help you with the redox. Oil rig. So basically, oxidation is loss, reduction is gain of electrons. Or Leo the lion says good. That's how I used to remember it all the time. So basically, Leo, loss of electrons, oxidized, and then Gur is basically gain of electrons, which is reduced. Now, I got some examples right here where we have molecules, and we need to isolate and sort those molecules into their oxidized and reduced forms. Okay? So, right here, I'm just going to go through them one by one. We have an electron, so we are gaining an electron. That means it's reduction. Q, right here, we don't have any electron with it. It's one thing. That means it's oxidizing. NAD, and then we have this. That means we lost an electron. That means it's oxidized. Now moving on to this, you see how we have two hydrogen atoms now, two hydrogen ions. So that means it's reduced, it's gaining. Moving on, right here, NADBH, H right here is extra. That means it's gain of electrons equals to reduction. And then right here, we lost an electron. That means oxidization, loss of electrons. I hope that made sense. Now moving on to photosynthesis and aerobic respiration. So basically, photosynthesis is conversion of solar energy, carbon dioxide and water into glucose and oxygen. Aerobic respiration is basically the oxidation of glucose to carbon dioxide and water, releasing energy for ATP synthesis. Right here, it's basically showing conversion of carbon dioxide and oxygen and water into glucose and oxygen. And right here, it's showing me aerobic. That means we have the conversion of oxygen and glucose into carbon dioxide and water. So now we have oxidative phosphorylation and ATP synthesis. So glucose oxidation yields 24 electrons that travel through electron transport chain. Energy from electron flow drives ATP synthesis, producing 32 ATP per glucose. Okay. Now we have the thermodynamics of chemical reactions. Gibbs free energy, basically delta G, it's basically the amount of usable energy at constant temperature and pressure. Remember that, that's key. So Gibbs free energy is basically the energy at constant temperature and pressure. Now we have exergonic meaning that delta G, oh, where's my laser? Meaning that delta G is less than 0. It's negative, and it's going to be spontaneous, not spontaneous, but it's going to be irreversible. Okay. Now we have delta G greater than 0 right here. It's non-spontaneous. Actually, forget the reversible and irreversible. We're going to learn that in glycolysis later. Now, talking about the enthalpy. Enthalpy is basically delta H, and it stands for heat content. It basically reflects the bond energies, okay? We have exothermic, where delta H is less than 0. Heat is being released. Remember that. And then we have endothermic. Basically, delta H is greater than 0 and heat is being absorbed. The units are joules per mole. Now talking about entropy. Entropy is basically the measure of disorder, and the symbol of entropy is delta S, okay? If S is less than 0, the system becomes more ordered, okay? And if delta S becomes greater than 0, the system becomes more disordered. We have an increase in entropy. The units are basically joules per mole per Kelvin. Now, talking about the relationship between Gibbs, enthalpy, and entropy. Okay, this is the relationship between the three of them, where delta Gibbs energy is equal to enthalpy minus temperature and entropy. Okay, I hope that made sense. And we're talking at constant pressure and temperature. Spontaneous reaction must have delta G greater than 0. Now let's talk about the spontaneity of a reaction, okay? So right here we have all the signals. If delta H is negative and delta S is positive, then the overall gain, like the overall sign of delta G, is going to be negative, okay? And that makes it spontaneous always. Now, if delta, so basically a negative delta G, that means that the forward direction is favored in a reaction, meaning that the products are more favored than the reactants at equilibrium, and that the reaction would proceed from the reactants toward the products without needing any external energy input. Okay, moving on. If delta H is negative, delta S is also negative, then delta G is going to be negative, but if T temperature is low, okay, and that makes the reaction spontaneous, but it's temperature dependent. Moving on. If delta H is positive, delta S is positive, then the sign of delta G is going to be negative, but when temperature is high. Because remember that delta G is basically equal to delta H minus T delta S. So if the temperature is high, then delta G is going to be negative. making it spontaneous but also temperature dependent. Now let's talk about the final situation where we have delta H as positive, delta S as negative, then the sign of delta G is going to be positive, meaning that it's not spontaneous and it will prefer the reactants over the products. So the sign of delta G is determined by the combination of delta H and delta S. Temperature can reverse. So temperature can reverse the spontaneity when signs are opposite. Okay? Great. Moving forward. So we have equilibrium constant and Le Chartier principle. Okay? The equilibrium constant, KEQ, is basically the ratio of product to reactant concentrations at equilibrium. It stands for this equation right here, concentration of products over the concentration of reactants. If conditions change, such as concentration, temperature, pressure, the system shifts to counteract the disturbance, which is known as Le Chartier's principle. Now, talking about Gibbs energy and chemical equilibrium graph. Right here, we have the exergonic and the endogonic. So, they're both exergonic reactions. I'm sorry, guys. Let me just pull out a very quick picture explaining the Gibbs energy. One sec. Okay, so basically this is a graph I built up. We have the negative, which is exothermic. We can tell that Gibbs free energy right here. We are starting from the reactant and we're making our way through the products and we're losing energy. Moving on to Gibbs free energy, but endothermic. We have the positive right here. Basically, we are starting with our reactants and we're moving up towards our products, meaning we require energy. That's about it. Moving on to the notes right here. We have the standard Gibbs energy in biochemistry. So I'm going to explain that in detail. We'll start with the standard state. Okay, continuing. So basically what we mean by biochem is basically like the standard state is meaning that delta G is going to be at pH of 7. And then the standard Gibbs energy is going to be noted as delta G prime dash, okay? So that is going to be, when you're given that, it's going to be the value under those conditions. pH 7, water 55.5 moles, and magnesium ion 1 millimole, okay? And it relates to the standard equilibrium constant delta K, okay? Now moving on, we have example calculation. We have the phosphate glucose phosphate equilibrium. The reaction goes as follows. We have the glucose 1-phosphate, which is being transferred to glucose 6-phosphate. We have the initial, which is 20 millimoles, and then we have the glucose 6-phosphate, which is 0 millimoles. At equilibrium, 25 Celsius is the temperature. pH 7, glucose 1-phosphate is 1 millimole, and glucose 6-phosphate is 19 millimole. It's telling us to calculate delta G, okay? So basically the way we are going to perform this calculation, so our R value right here is going to equal 8.314, okay? That's your R value. So this calculation is going to be as follows. So 5 joules per mole Kelvin. Okay, so that's the unit for the gas constant. Known as R. Now, for this calculation to be performed, we are going to have our delta K equilibrium, which is equal to glucose, the concentration of glucose, the products, okay, over the concentration of the reactants, okay. Now, we have the products is given to us, which is 19 millimole and 1 millimole, okay, which is equal to 19 millimole. Now, calculating delta G, so I'm just going to make it right here. Delta G, the biochemical standard delta G, is equal to negative R temperature, the gas constant, ln K equilibrium, okay, which is equal to negative 8.315 joules per mole Kelvin times 298. Remember that the units have to be in Kelvin, so basically the units have to be in Kelvin for temperature, so they cancel out, okay. Next, it's going to be ln 19. That means that my delta standard G value is going to equal to negative 7.3 joules, but we're going to turn that to kilojoules, okay. We're going to turn joules to kilojoules per mole. Good? Good. Moving on, we have that the general expression for this is going to be basically delta G equals to negative RT ln equilibrium plus RT ln of concentration of products over the concentration of reactants. Hope that makes sense. Now, moving on, basically right here, if delta G is less than 0, the reaction proceeds forward. If delta G is greater than 0, its reverse direction is favored, okay? Now moving on, we have the mass action ratio known as Q. Basically, Q is the product activities over reactant activities, meaning current concentrations. So, comparing Q to the equilibrium constant, we know that if Q is less than the equilibrium constant, then delta G, like the reaction will be proceeding forward and it's going to be product forming direction. Delta G is going to be less than 0. And if it's greater than the equilibrium constant, then delta G is going to be greater than 0, okay? So, in summary, Q and G are proportional, okay? Next. So basically, Q reflects the actual concentration of reactants and products under steady state conditions. such as in living cells, can bring those with the equilibrium constant. So as we already explained, we have that it's going to be product forming, prefers the forward. We have if Q is greater than equilibrium constant, it's going to be reverse reactant forming. And then if Q and K is equal to each other, the system is said to be at equilibrium. Now we have core thermodynamic equations right here. The standard Gibbs energy is equal to that. The actual Gibbs free energy is equal to that. And then at equilibrium, we have delta G is equal to 0. And then we have the Q, mass action ratio, is equal to the equilibrium constant. These connect directionality of a reaction, giving us delta G sign with the measured concentrations Q and intrinsic probability reaction K. Okay? Now, moving on to the ATP, the cellular energy carrier. ATP, known as adenosine 5-triphosphate, it's a primary carrier of chemical energy in living systems. Hydrolysis of its phosphoanhydride adds bonds release free energy. Okay, under standard condition, it's going to release negative 30 kilojoule per mole. Now we have the following diagram, which shows us the alpha, the beta, and the gamma phosphate groups linked by high energy phosphoanhydride bonds. Okay. Now, adenine base with ribose, the delta G values of hydrolysis for each bond are indicated, illustrating the stored chemical energy. So if we have the alpha bond right here, we have the chemical values right here, delta G values indicating. Now, energy coupling, we have ATP hydrolysis provides exergonic drive, meaning unfavorable. If endergonic, it's going to be unfavorable biochemical reactions. Phosphate donor, the gamma phosphate can be transferred or substrates, generating phosphorylated intermediates that participate in metabolism, signaling, and transport. Now, glutamine synthesis, two-step ATP-driven pathway. Biosynthesis of glutamine, meaning anaplasm from glutamate, proceeds via glutamine synthesis in two sequential steps, each powered by ATP. We have first activation or phosphorylation step, and then we have amidation step. So the phosphorylation step, where we have glutamates combined with ATP, giving us glutamyl phosphate plus ADP. Okay, it's highly exergonic phosphoryl transfer. It's activated intermediate known as glutamyl phosphate. Okay, next we have amidation step, where we have the glutamyl phosphate right here plus ammonia under glutamine synthetase, which is an enzyme, giving us glutamine and inorganic phosphate. Basically, the carbonyl group, the activated carbonyl group, will attack the ammonia, forming glutamine and releasing inorganic phosphate. Overall, the free energy released by ATP hydrolysis drives the formation of glutamine and is essential for nitrogen donor and biosynthetic pathways. Now we have the balancing between catabolic and anabolic fluxes. In metabolism, we have catabolic, meaning the breakdown, and anabolic, building pathways, maintaining the dynamic balance of energy carriers and biosynthetic processes. Now we have the key points, which is cataplasm provides energy, ATP, and reducing power, NADH and FADH2. by oxidizing fuel molecules. Endoplasm consumes energy and reducing equivalents to assemble macromolecules needed for growth and maintenance. Steady state is achieved when a net flux of ATP synthesis equals the net ATP consumption, and the pools of oxidized and reduced coenzymes remain constant. A final summary of the relationships between Gibbs energy. So right here we have the standard Gibbs energy known as delta G naught, which is negative RT ln K, and the actual Gibbs energy known as delta G, which is delta G naught, the standard Gibbs energy, plus RT ln Q, okay, mass action ratio. And then the reaction direction, we have it's determined by delta G. If it's negative, it's spontaneous, meaning it's going to go forward. Now we have energy carrier, it's known as ATP. The hydrolysis release, it's negative 30 kilojoules per mole, and it drives endergonic processes. And then we have the flex balance, catabolic ATP production, anabolic ATP consumption, and set the steady state. Perfect. That's it for lecture. For this lecture, we've covered the physical biochemistry review. Thank you. Have a good day.